Okay, good morning and welcome to yet another class in our machine learning series. So today we'll be looking into decision tree. I hope you can see this tree. I tried to, visualize something. So you can see a tree, right? Remember we always say that a picture is worth more than 1,000 words. So I thought of finding why. I know you are used to this, okay? You know this very well. And you can actually see that tree has some prominent features, right? You have the root, you have the stem, then or your main branch, and then you have your branch, and then you have the leaf, right? Right? So there you got the leaf. So you can as well see the leaf here, right? And so this was another branch. So we'll be looking into decision trees, right? So in machine learning and even in data mining, and generally even in your basic artificial intelligence class, you must have learned about using decision tree to make some salient decisions, right? So in life, we make decisions almost every now and then. Decisions about where to go, what kind of clothes to put on, what should I have for breakfast or lunch or dinner, whether I should accept a job offer or not. There are lots of decisions we make, right? So looking at this, why can't we somehow model this so that by using some algorithms, we'll be able to understand how actually decision tree works. So you see, as a representation here, you can see the root, right? And then you see your stem, goes to branch, and the leaf. So is it that this is what you are going to do in decision tree? Something similar to that, okay? So this really mirrors whatever you've seen there. So how can we define a decision tree before we look into the algorithms? Yes. So for most of you that want a definition of a decision tree, okay, so I just want you to see the algorithms first, and then we will define it, okay? So let's give a small definition, okay? So a decision tree, you can see it as a tree in which each node represents what? A feature or an attribute. Okay. So now I've told you only about stems, the main stem and the branches and leaf. Now I'm talking about nodes and attributes. Let's define this again, and then we take an example that will look like a decision tree, okay? So decision tree is a tree in which each node represents a feature. So a feature is known as an attribute, or simply put, your columns, okay? So each node represents a feature, right? And each link, remember here I have to make decision now, whether to go to this one or to that one. So each link represents what? A branch, okay? So then that branch is our decision rule. And each leaf, this is a leaf, right? Represent an outcome. So let's forget about the loss of explanation and just define it once again. So a decision tree is a tree in which each node represents a feature or an attribute, and each link or branch represents a decision rule, and each leaf represents an outcome. So let's make a small decision tree whether to accept a job offer or not. Please remember, I will superimpose this, okay? Leaving this tree here, maybe it will be cluttered. Why don't I erase this now? Now we've seen this, right? So keep that in mind. What are we going to see now? We're going to see nodes, right? Attributes, and what? Leaves, right? So the node, you call it as your root node. So usually we say here, this is the root node. Okay? So this represents your what? Your decision rule. Decision rule. And this represents your what? Say outcome. Now I'm going to superimpose something on this, okay? So let's say we want to make a decision tree whether to accept a job offer or not. A simple decision tree which everyone can make. So what will be your primary root node? Can anybody tell me? What should be your primary root node? See, most of us will look at the salary first. Before any other constraints, we check the salary. So you have decided that the salary is what you're going to consider. So salary is your root node. right? Fine. If salary is your root node, what are you going to consider next? Now, how much is the salary, right? So, I'm going to expand this now. Instead of just writing salary alone, I will make it this way. So, this is salary, and it has a constraint. Is this salary greater than 4 lakhs per annum? For most of you. Even freshers also, they want 4 lakhs per annum salary. Anyway. So, if it is greater, oh my goodness, I will not even consider anything. Maybe I will accept the offer. Now, so the company tells you, see, because of the pandemic, we are running into financial crunch, so it is not greater, right? So, is this greater than 4 lakhs per annum? No. Immediately, what the student does is reject offer. Reject. So, this is my leaf node, right? So, this is my leaf. So, this is a pure outcome, right? So, I'm already done with this. It's not greater than 4 lakhs per annum. Why should I accept the offer? I rejected it, so I've reached my leaf, okay? Or my pure outcome. Now, if it is greater, again, you say, okay, fine, let me go think about it. Because my mom may not want me to leave Mysore. She wants me to stay in Mysore only. Now, if it's greater, now I will check what again? Maybe I check work location, right? So, work location, maybe I translate it into the average time it takes to reach to my place of work. So I might check work location. Work location. Is it in Bangalore or in Mysore? In Mysore? Question mark. If it's in Mysore, what I will do, yes, I will accept the offer. What again I will do, see, again I've come to a pure leaf node, right? A possible outcome. So what I will do, I will accept happily. So I've accepted the offer. Now this is again a pure leaf node. So I don't need any further division, right? So otherwise I will stop here, okay? Otherwise I will reject the offer. What I will do, I will reject. What can you see now? This one, that, and that. These are all my pure nodes, right? My pure leaf nodes. So there is no further division. But the problem arises where, you know, we want to know which one is the root node. Which one should we take as the root node? If salary is my constraint, how about work location? For most people, work location might be the constraint, right? So I need my work location to be my root node. Now, how about, okay, work location is in Bangalore, obviously I will stay there. How about other facilities? Will they be providing bus facility? What are other incentives that the company will be giving? So many of us, especially for the married people, they always consider all this. How will I be far away from my home? My child is so small. My husband needs my attention. My mom needs my attention. My dad needs, you know, all kinds of stuff we have to consider. So you see, knowingly or unknowingly, we make decisions, right? So now the question arises where we have to decide which one becomes the root node. And that's where we have to look into some algorithms, okay? So we look at the algorithms which can enable us to do this stuff, okay? So we know that we have primarily, okay, at this level, we can talk about cats and dog, right? Not cat and dog, okay? CART stands for classification and regression trees, and ID3 stands for iterative dichotomizer version tree. So what you should understand is, apart from CART, we also have other algorithms. So we also have C4.5, where C stands for classification, and we also have C5.0. So these are series of algorithms that are developed by Ross Quinlan, R-O-S-S. So Ross Quinlan, okay. So Ross Quinlan developed these algorithms, okay, that we use to generate a decision tree from a sample data set. Now, when we talk about classification and regression trees, we talk about what we call Gini index. Okay, it all depends on how you pronounce it. Maybe Gini index, I'm not an English scholar. Gini index or Gini index, okay? So Gini index or Gini coefficient or Gini ratio is a statistical measure of distribution which was developed by an Italian statistician, and obviously it was named after him. His name was Colorado Gini. Why I said was because he developed this in 1912, so I'm pretty sure he's no longer alive now. So it was used to gauge the economic inequality of a population. But are we talking about economics here? No. So in data modeling, the same Gini index was extended to measure the inequality amongst values of a variable. So what are we talking about here? We are talking about how whether a variable is homogeneously distributed or heterogeneously distributed. We'll get to this later. When we talk about a pure sample, we know that those samples they contain of the same type. We will see that when we take a sample data set that will decide whether a game should be played or not. Where we have a pure sample of all yes, 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 yes. So the Gini index can be 0 or 1. And we can represent this in form of, since it's a ratio, right? Ratio can also be represented in form of what? Percentages. Please remember it ranges from 0, okay, to 1, where 1 represents an impure data or subsample, okay? And then 0 represents what? The pure subset. I will repeat this again. See, when we have a purely homogeneous subset, and I know you've studied this even in your sciences, homogeneous means it contains the same type. Example, in the data set, if we are talking about a sample that purely has only yes, 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 yes outcomes or true outcomes, then we know that that is a pure sample. So if they are equally distributed, so in statistics we say equiprobable, where we have equal chances of yes and no, equal chances of true and false, we will say that they are what? A purely impure. Okay, I can't say purely impure, okay? They are impure. So, keeping this in mind, we will not look into CATs, okay? Classification and regression trees. We will look into ID3. Remember, ID3 is just ID stands for iterative dichotomizer. So what is iteration? Okay, you call it anything, iteration, iteration. So iteration is just about you see repetition, right? So you've written recursive functions, okay, functions that cause itself iteratively. So you see repetition. So what about that? How about dichotomizer? So here it is a successive division, I beg your pardon. Iteration means what? Repetition. Dichotomizer is division. So it keeps repeating by dividing the entire entire data set into subsets, okay, and calling the functions until we get a desired tree, okay? So, or we get the desired pure subset. So, when we talk about ID3, we have three primary functions that will enable us to compute that will enable us to get to the desired tree. So the first we look into is the entropy function. So entropy, again, we must have studied in sciences, right? Okay, or it's just an English word, which means what? The rate of disorderliness, or degree, not rate, of disorderliness or randomness. So a pure sample has almost a negligible entropy, whereas an impure sample has a very high degree of entropy. So when we talk about entropy here, we are talking about how pure, okay, how well the sample is represented, right? So that we will compute by using a function. So this is it. It's a very simple thing. If you look at it here, we are saying it is represented as negative what? P positive, C, minus plus or what? The positive samples, then positive sample of that to base 2, right? Log of the positive sample of that to base 2. Again, minus, see, you have what? Negative samples, number of negative samples, into negative samples to what? Base 2. Now, this maybe you think is little confusing, so we expanded it this way. So you have all the positive samples, say example. So I will give you a small data set and then we will just look into that, okay? So you have this, right? So all the negative samples, fine, divided by the total, right? So if you happen to have a data set that consists of, say, 5 positive examples and 3 negative examples. So why can't we substitute values now? So say the data set has 5 positive examples and 3 negative examples, right? So what will this be now? This becomes 5 upon 8, right? Because C 5 plus 3, okay? Log, remember, okay? So again 5 upon 8 to base what? 2, right? Minus, now we are going to talk about the negative examples here, right? So the negative examples here, remember negative is 3. So we say 3 upon, again 8, right? Denominator remains the same. Then again 3 upon 8 log base 2, right? Now, this is what we are going to compute. So this is explicitly what that formula is telling us. Now, after that is done, we compute the average information entropy. So if you look at it this way, again, it might look like it's confusing. But don't worry, we will take example and then you will get to know this better. So here we are talking about, see this entropy? This entropy is rated as entropy A, whereas this entropy S. So entropy S refers to the entropy of the entire data set. And that of A refers to just what? That particular attribute which we are talking about. So we will expand that later. And please remember, P of I and N of I refers to that attribute, like in the bigger table we have made a smaller subset or a smaller table. So from that smaller table, the P and the N's of I becomes the P and N's of that smaller subset. And then the same P and N is from what? The larger table or the other data set. Now into the entropy of A. Fine. After that, we calculate the information gain. Please note, we will decide, okay? The decision boundary is drawn based on the information gain. So the one with the highest information gain becomes our root node. But please remember, we cannot just jump directly to the information gain without computing what? The entropy of the entire data set and average information entropy. You can see it here, right? So information gain is expressed as the difference between the entropy of the entire data set and what? The average information entropy. That's why we see that it is what? Entropy of S minus I of attribute. And you can see it here. Okay? So the algorithm looks like this. We compute the entropy for the entire data set, which we call entropy of S. Now, for every attribute or feature, we calculate the what? Entropy for all the values, right? And then we calculate the average information entropy. Then we calculate the information gain for that current attribute. And after this is done, we will now make a smaller table, right? It's usually better if we visualize this in form of a table. So there we compare, we express all the values of the what? Information gain for the respective attributes. So the one that has the highest information gain becomes our root node. So if we get back to this, say I have to decide between whether salary or work location should be my root node, okay? Okay, or work location should be my root node. So there are a number of possibilities here. I have started with salary, and that was my root node. I started with work location. If I start with work location also, again, I can also check whether to accept or reject the offer. Apart from that, how about incentives? So how about working conditions? See, will I be always transferred? Say I'm in Bangalore today and they tell me, so, no, we have a job in Bombay or Pune, you have to go there. See, you see, the company should tell me most of the things up front, right? So how about the work timings? So should I be working night, okay? Would I be on rotational shift? Or is it kind of a fixed thing where I am sure that 90% of the time I'll be working during the day because I'm more productive in the daytime, right, than at nighttime. So for some people, the work timings might also be a primary factor. So if that is a determining factor, what you have to do again, I also put that also as an option, right? So I'm going to put what? Work timings. So in all these three now, so which one is the best? Okay, where should I start splitting the tree? So because of that, we use the ID tree algorithm, right? So, and then after we have computed the information gain for the current attribute, so we pick the one with the highest gain. Okay, so from there we start splitting the tree. And how long will we do this? We have to repeat this process until we get pure leaves. Now, what happens when we don't get pure leaf? Okay, or what happens when that doesn't converge? Because we can do this n number of times. Remember, it is called iterative dichotomizer. It's successive division. It will keep happening, okay, repeated division n number of times. How long will it go on? If the tree is large, if the data set is large enough, because even you will see here when we take this data set that has about 14 samples, okay, 14 records, and it has about 5 attributes. You see, it takes, for an average student, it takes minimum 30 to 45 minutes to compute the entire subspace. So think about if we have a data set that has about maybe like 1,000 attributes. Okay, sorry, 1,000 records. I'm talking about rows now. Okay, and maybe about 10 attributes. Because in real life, real life data, they're always messy and heterogeneous, right? Consisting of all kinds of stuff, including your missing values also. So in that case, will I do this? Will ID3 work? That's what my question is. So you see, the larger the sample space, okay, or the number of records you have in your data set, the more it takes time. So what happens if you don't arrive at a pure leaf node? What happens now? So you know that there might be some attributes. I don't want to say overfitting now because it's too early, okay? There might be some attributes that are not really necessary, okay? So what do? We need to go back, view it like now like a water flow, right? A water flow model, right? So we started from celery and then we moved down until we get here, right? So reaching here, we still know that we did not get pure leaves. So what do? We have to backtrack, right? So that process of backtracking, going back and tracing which attributes really contributed to this or whether they really contributed to this or not is known as pruning. And that's where CART comes into play. CART, classification and regression trees. So we tried with ID3 and we saw fine, we are not arriving at a proper answer. Then we get back and use what? CART. Okay? Hope that makes sense. So what we'll do next is we will take a sample data set, right? And then we compute all this, okay? Line by line. And yeah, it's always better if you grab your pen and paper and you follow along. You can always pause the video, okay, and then do that later. But it's always better, when we start, you also start with us, okay? All right. Okay, guys, please, we want to continue with where we stopped previously. Remember, I was telling you that I'm going to show you a kind of a sample data set, right? And then we will try to apply all the processes which we saw, right? So, please don't forget, we just discussed about decision tree and why it's actually needful. So, if you want to actually visualize how a particular problem can be solved by using a constraint. So what's the constraint now? Which one is my root node? That is my constraint, right? So we can actually solve this using a decision tree. And if you check even in data modeling, on machine learning, or data analytics, most of the problems are solved, classification problems, okay? They are solved by using decision tree. Many of them. Even there are variants of that also where people go and use random forest. That is okay, it's not part of the syllabus now, but if you remember, almost every problem, I'm not saying all, okay, I'm saying almost. So every problem can be modeled using a decision tree. And we've seen this, right? Just to refresh your mind, we saw two major types, right? Where we had CART, classification and regression trees, which uses your Gini index, and we have defined what Gini index is. And then another one, ID3, which stands for iterative dichotomizer. So your class is purely on ID3. So ID3 for me is cumbersome because you will understand when we start solving this. See here, we have about 14 rows, okay? So you can see it from there, right? Using the ID number. About 14 rows, and how many attributes or how many features are here? So if you want to take entire thing, so you see 1, 2, 3, 4, 5, 6. But please, okay, do we need the ID number? Do we need it? We don't need the ID number, right? So, and I've not given you instruction on what to do. So, my instruction is, given this tree now, I want you to, given this data set, I want you to decide whether tennis will be played or not based on these conditions. So, what you have to do now is, you need to find out what influences playing of tennis. What is it? So this becomes our predictor class, right? So this now is what decides. So what we can do here is, we don't need serial number. You think once again, will this have any effect? No. So I'm going to strike it out. So I strike out this. So how many features are left? How many features are left? 1, 2, 3, 4, 5. But wait a minute. This is our predictor, right? So this is where the emphasis is. So I know that now I have what? 4 features. 1, 2, 3, 4. Getting back to our decision tree, the next question arises, which one is my root node? Where should I start from? Should I start from Outlook and then consider all the other attributes of Outlook? Or should I start from temperature and consider all the attributes of temperature? Just in case, Outlook has 3 more attributes: sunny, rainy, and overcast. And if you check, sunny, overcast, rainy, right? So now you go to temperature, hot, mild, cool. It's okay. See, somehow we got the data set, right? So we don't want to say whether this data set is a true representation of a problem which can be solved with a decision tree. We have to try, right? So we cannot just conclude without trying. So again, we look at humidity. You have other ones: high, normal. Okay, so only 2, high and normal. We look at windy. Windy can be weak, strong. That's all. Again, 2. And you have your play tennis, yes or no. So let's recall how we solve this. So first, we have to compute the entropy for the entire data set. Please, I'm sorry if you're not able to see beyond this, okay? If you're not able to see beyond this, I'm reading it out so that you won't be left behind. See, first step, I hope everybody can see this. First step, you have to compute the entropy for the entire data set. And you know the formula, right? Fine. So next, for every attribute or feature, say example, we have taken Outlook. Let's start from the first one, okay? So what are the attributes of Outlook, or what are the features? Sunny, rainy, overcast, right? So for every attribute of this Outlook, we have to calculate their entropy. So since it's a subset of the main entropy, please remember the entropy of the entire set is designated as entropy of S. Entropy of the subsets is designated as entropy of A. So for the entropy of S, we are going to use entire sample. So for the entropy of A, we are going to use a more reduced table, and you will see that now. After that, we calculate the average information gain. We calculate the gain for the current attribute. So we pick the highest gain attribute. And since it is iterative, we repeat this process of subdivision, dividing and checking, taking out the one which has the highest information gain until we arrive at a pure leaf. So I'm going to wipe this now, and enough of talking, we get started. All right. So first thing what we have to do, we need to consider how many positive examples are there. You have to tell me. Please, I still request all of you to somehow pause the video, start solving. Afterwards, you just cross-check. See, if you check if you talk to your seniors also, we do this in class, right? So I want you to pause the video right now and take your pen and paper. Don't say, okay, I'm wasting. Actually, even I wasted time writing this, right? So why can't you waste that time and write it? Please remember, we are not wasting time. What you call wasting time, see, we actually trying to, reinforce whatever we have learned. Okay, so because you were not able to see the board, I've decided to rewrite it again. So if you see here, we arrive at this, that all the positive examples, we got 9 of them. You can check again, you can cross check, okay? And then for all the negative examples, we got 5. So what's the sum of them? P plus n is what? 14. So let's plug in the values here now. So we have minus p upon p plus n into p upon p plus n log base 2 minus n upon p plus n into n upon p plus n log base 2. So we solve this and then we are able to get 0.940. Now, please remember this is the entropy of S. So what do we have to do next according to algorithm? So we move to now this enters step 2. So in step 2 it says for each attribute, for each what? Attribute. So for each attribute means what now? So say for each attribute, what do you think we want to compute? You guessed it right. We want to compute entropy of A. So for each attribute, say now we have to choose, what are the attributes here? Outlook, temperature, humidity, windy. Outlook, temperature, humidity, windy. So let's take now outlook. So if we take outlook, please remember, for each of that, we need to calculate entropy of A. So for we to calculate the entropy of A, what are the entropies of A now? Entropies of A means what? The subsets or subgroups of this attribute. Subgroup of this attribute outlook, which is sunny, overcast, and rainy. So we need to calculate the entropy of entropy A for what? Tell me. Sunny, overcast, and rainy. Overcast and rainy. So how would this be possible if we don't make a smaller subsets? So what we do now is we make small tables, okay? So here we take outlook as the what? A column against what? Play tennis as our predictor. So in that case we have now sunny, rainy, and overcast. So let me try to fit it in here before I wipe the board. All right? So I hope you've taken this table, because after this session, I'm going to wipe this, okay? And then we start another session. Please take this down and then walk along with us. Fine. Now, here we have to make now what? Smaller tables, right? So here I have outlook, and I have play tennis. For which one? Outlook, play tennis for sunny. So please tell me, sunny, how many sunnies can you get there? 1, 2, 3, 4, 5. Right. Sunny, 2, 3, 4. Sunny, 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 and sunny. Now, let's check their equivalents. Now, if we go to play tennis, for the first sunny, it was no. Second sunny, again, it was no. So first sunny, nahi. Second sunny, nahi hai. Third one, what do you have for sunny? Please go with me. Sunny, yes. No, sorry, that was rainy. Sunny, no. Sunny, yes. And sunny, yes. So I have no, yes, yes, right? I have no, yes, and yes. So you see the reason why I want us to do this together. I hope you can see this. So this is for the smaller subsample of what? Attribute outlook. Now, again, see, I need for overcast and I need for rainy. So let me try to fit the tables here. Next one, this is for overcast. Oh, I think you won't be able to see if I go that way. So sunny, I'm going to reduce this small again. So next will be what? Overcast. Now I'm going to compress it, okay? Just bear with me. Overcast, and the last one will be rainy, so that you'll be able to see. Okay? So, again, so this is outlook, as you already know. And then this is play tennis, I'm calling it PT. This is again is outlook. I'm calling play tennis PT. Or in your your high schools or whatever you did this, right? I mean, PT, physical training. Elementary school I'm talking about, not high school. So PT, yes, play tennis. Now, let's take all the other attributes also. 1, 2, 3, 4, 5. Again, 1, 2, 3, 4. I'll tell you why. See, I know that total number of records here, or rows here, or samples here, okay, they are 14. I've taken 5, right? One will be 5, another one will be 4. Ashte, fine. Now let's go to the one, I think. Now the next one is what? Overcast. Overcast, let's see. 1, 2, 3, and 4. Overcast. 1, 2, 3, and 4. And I know that all the overcasts are yes, 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 yes. So I go here, overcast, yes, 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 and yes. So this is overcast. Right. Now, the next, what is left now is what? Rainy, right? So obviously rainy will be 5. Yes, I hope you agree to that. So rainy, 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 rainy. Now, let's check the equivalence, okay, in play tennis. So let's go there now. Rainy, the first occurrence of rainy is yes. Second is yes. So let's put them before we forget. Yes, yes. Now, third of rainy is nay, no, fine. The fourth one, rainy, is yes, and fifth is no. So we have yes, and fifth is no. So, right. So we are done with this. So next thing we have to do now is to what? We have to compute now what? The entropy of each of these, right? See, outlook for sunny, outlook for rainy, outlook for overcast, right? So for that, I have to wipe this. Fine. Give me a second. All right, welcome back, guys. So what we have to do now is we have to calculate what the entropy A of all this. So can we write it this way? Entropy of, so we are going to calculate next. Entropy of what? A, right? That is entropy of what? Outlook, no? That is my A. What is that? Respective value of the outlook, right? So the first one, what we have to do is entropy of sunny. Are you there? Fine. Please, the formula is still there, okay? It has not changed. So we call it entropy of outlook. So permit me to use something else. Entropy of outlook equals, let's plug in the value now, sunny. So what do we have? So sunny, how many positive examples are there? Please be very careful. Remember now, when we are calculating the sub-samples, we cannot use P plus N of the entire data set. That's why we made this table, right? Fine. So let's check now, how many positive samples are there? So I'm going to put it here, plus positive. How many of them? Quickly. 1, 2. So obviously, negative samples will be what? 3. No magic, right? So this is what we are going to plug in now, quickly. So we plug in the same value there, which is what? Minus 2 upon 2 plus 3 is 5 log base 2 into 2 upon 5. Then minus negative samples, 3 upon 5 log base 2 upon, again, 3 upon 5. Okay, so grab your calculator and punch the stuff. Okay, evaluate this quickly. You will see it boils down to 0.971. We have to repeat this again for what? Outlook, right? Outlook equals what now? Rainy. Rainy. So for rainy, let's go there quickly. So positive samples are 3, negative 2. Please don't get confused now. Please look here. Here positive samples were 2, negative 3. Here is just the reverse, right? So positive samples here will be what again? P3. P positive is 3. P of negative is 2. Now, same thing here. We now see minus 3 upon 5. Log base 2 of 3 upon 5 minus then 2 upon 5 log base 2 of 2 upon 5. See, don't you think this will be the same answer? I mean, if you compute this, don't you think it will be same? Are you with me, guys? You check. It's going to be the same. So we have 0.971. Now, the last one, I mean, for this subset is outlook of what? Overcast. So, remember what I told you, right? In the previous class that, I mean, yeah, in this class, only not previous class, that the entropy can be, entropy ranges from 0 to 1, right? So, when we have a purely heterogeneous set, meaning we have only one instance, it is what? 0. So, it's a pure sample. So, if we have equally distributed, say 50% of true situations and 50% of negative situations, we have an equiprobable event where we have 0.5 in both cases. Now, what if, okay, there are no occurrences of this? See, please remember, if there are no occurrences of that, we have a pure set, right? Fine. So which is what? 0. And it is highly impure when we get what? Entropy of 1. Remember how we defined entropy, right? It's just a what? A term used to show how varied, okay? Or how impure your, or how, yeah, how impure your, I don't want to say substance, you are not in a chemistry class. How impure your data set is. So here we have now, we don't need to compute this, but if you like, you can compute it and the entropy is 0. So let's check, So we have here, since there are no negative examples, right? So only positive are there. So we have what? Minus. So what do you get now? 4 upon 4 is what? Minus 4 upon 4, you tell. Is 1, right? Log base 2 of what? 4 upon 4 minus, the rest is 0 only. No, we are multiplying, so this is gone, right? So if you check minus log 1 to base 2, you will get 0. Fine. So that's how we get this. Fine. So this is done. Now, if you remember, after this is done now, we have to pick what? Go back. We have to pick what? Tell. You are wrong. You cannot pick the information gain. See, that's why you guys are not listening. You can't pick the information gain now because you have not computed it. So, you are not picking anything. You have to compute now what? The average information entropy. So this enters our what? Subset of the step 2. Step 3 is where you pick the highest gain attribute. Okay? So here we calculate what now? Average information entropy. So calculate now. See, this is lengthy as you can see. So we calculate average information entropy. Calculate average info entropy. So how do we calculate this? If you remember that formula, right, it says I of, remember, attribute, right? I of attribute. So I of, what's the attribute now? Outlook equals what? We saw summation. If you remember, we saw this sign, summation of Pi plus Ni upon P plus N. Did you remember this? Into the entropy, right? Did you remember this? So this we have to expand now, okay? So let's expand this formula. This becomes P of what now? See, P of what? Sunny, rainy, and overcast, right? So we are adding them. So that is summation. So this becomes P of sunny plus N of sunny, okay, upon, please remember, upon P plus N, that was what we saw, okay, into the entropy of what? You guessed it right. Entropy of sunny, and that entropy of sunny is from outlook equal sunny. Did you agree? Yes. Plus is summation. Same thing we have to repeat. P of what? P of rainy plus N of rainy. I'm taking pains to write this so that you also do same. The more you write it down, the more you remember. P plus N into the entropy of, again, outlook equal rainy. That's not over. Plus the last one, P of overcast plus N of overcast, okay, upon P plus N. I hope you can see the board. That's why I'm also mentioning it alongside. Into entropy of outlook equal what? Overcast, right? So this is done. We have to plug in the values now. Okay, I believe, see, at this stage you have memorized the formula, right? So let's move on to plugging in the values. Okay, so for that I have to wipe the board. Please remember what the formula, what we got in the previous, what our previous answers were. So if you can't remember, fine. It's always good you make a table of the values, okay? So please remember, for the entire entropy was this. So we need P of sunny plus N of sunny. That is 2 plus 3 upon. Now the question is, when I say this, you know what I'm picking, right? So how about when I say P plus N? P plus N, I'm talking about the entire data set. So you have to use upon 14. Is that clear? Fine. So let's proceed. So I'm going to wipe this, and again we continue. So the first one, let's plug that in. So, so for sunny, if you remember, we had P plus N, right? So where our P was P plus N quickly for sunny, so which is equivalent to P plus N, which is 2 plus 3 upon 14 into what? Entropy of outlook equals sunny. Go back there. Entropy of outlook equals sunny, 0.971, right? 0.971 plus, so we get to this now, rainy, which is again 2 plus 3 3 plus 2 rainy. 3 plus 2, please remember, positive samples here were 3, negative 2. Okay? So 3 plus 2 upon 14 into, again, go back, rainy, 0.971. Okay? So I'm not going to go beyond this because you won't see the board. Right? So, again, plus the last one for outlook, right? So, for outlook, we had P plus N, and remember, the entropy was 0, right? Did you remember that? The entropy was 0, so I don't want to do this. Why? If I multiply anything by 0, okay, for the purpose of you guys, I will do it. 4 plus 0 upon 14 into 0. Whatever you get and multiply by 0, that disappears. So let's evaluate this. So after evaluating, we are going to get what? 0.693. Now, this is done. What have we calculated? The average information entropy. So what we need to get now is what? Information gain. So calculate information gain. So info gain, I'm going to abbreviate it, okay? Is the difference, right? Remember, entropy of what? You guessed it right. Entropy of S minus what? Don't forget, guys. Entropy of S minus what? Good. The average information entropy, which is I of the what? Attributes, which is what we just computed here. So what is the entropy of S? 0.940. So gain of outlook equals entropy of S 0.940 minus the average information entropy, which is what? 0.693. Quickly, tell me what the answer is. So what do we get now? 0.247, which is 0.247. Okay, we are done with this. Okay? Guys, remember, we are done with this. Let's recall what we did. First step, we calculated what? Entropy of the entire data set. Next, for each attribute, say outlook, we made a smaller subset. Okay? And we calculated each of their entropies, right? So after calculating each of their entropy, we calculated what? Average information entropy, right? We used this and we got that. After that, we found the information gain, which is the difference between average information entropy and what? The entropy of the entire data set. After this is done, we got outlook. But that's not over. This is just stage 1, or first step of the problem. We are done with what? Outlook, right? Attribute equals outlook. What happens to temperature, humidity, and windy? That is an assignment for you. So, what you have to do, please listen. I'm going to give you the answer. You have to trace it and check whether there are discrepancies, okay? Please remember, the same thing we have done for outlook equals what? Attribute equals what? Outlook. You have to do it. Remember the table I just wiped now? You have to do it for, you have to compute it for what? Why don't I write this? You have to compute it for temperature, humidity, and windy. So your assignment will be, now, so I'm going to wipe this. So you have to, next, repeat for other attributes. Attributes are known as features, okay? Or columns, that's it. Or columns, okay? So, you have to do this for other attributes. What are the attributes now? Temperature, humidity, and windy. That is for temperature. So, in temperature, remember we have sub-attributes. I mean, for you take like this, okay? Temperature, play tennis. In temperature, play tennis, you have to have 3 sub-tables again, which includes hot, mild, and cold. So, hot, mild, and cold. Same thing. That's why I left this table here. Please remember, in place of outlook, you substitute temperature. Okay? So you say temperature, play tennis. So first one, subset will be hot. Find how many instances of hot are there. Next, temperature, play tennis, mild. Lastly, temperature, play tennis, cold. Okay? Once you are done, you go and compute the what? Average information entropy, and finally the information gain for that one. So let's say I have calculated the information gain and then I'm getting 0.029. So I'm going to credit here gain of, oh, you will not see the board. My goodness. Okay, I'm going to tell the value, okay, 0.029. So I've calculated the gain, which is 0.029. Even if you don't see it, but I just mentioned it now, okay? 0.029. Now, after that temperature is over, you have to repeat the same process again for humidity. So you repeat for humidity. Make some subsets of that also. And for humidity, you have high and normal. So for high, you make again. And for normal also, you make another table. Okay? So same thing. Humidity, Platonese. Okay? For humidity, high. Then again, humidity, normal. Humidity. See, please remember. Humidity, Platonese. Humidity, Platonese. This will be for high. That will be for normal. Okay? Fine. So after that is done, they'll say the gain was 0.152. That's actually the gain, okay? 0.152. So this is the gain for that, okay? So 0.152. And lastly, you have to compute for windy. So windy. So in windy, what do we have? In windy, then you have strong and weak. Again, you repeat the same thing, strong and weak. So, and again, you calculate, follow the same process, calculate the average information entropy, calculate the information gain, and at the end, the information gain boils down to be 0.048, which is 0.048. Now, you enter step 4, okay? Sorry, yeah, you enter step 3, please. You enter step 3. The step 3 says what? Pick the highest gain value, right? So for me to pick the highest gain value, let's put this in a table. So I'm going to put it here now. So please look here. So what we have now is, I will call that attributes and the gain. So here I have attributes, and here gain. See, why am I putting it in a table? So it becomes easy for me to backtrack, right? So the attributes were outlook, if you remember, temperature, humidity, and windy. If you remember, outlook, temperature, humidity, and what? Windy, right? So why put them into their respective values? Outlook was 0.247, 0.247, 0.247. Next, temperature, 0.029, 0.029. Next, windy, 0.048, 0.048. And lastly, humidity. Humidity, 0.152. And lastly, windy, 0.048, right? So everyone knows that the one with the highest information gain becomes the root node. So which one has the highest information gain? That is outlook. So I circle it now. So with this, I'm going to leave you at the first stage of the tree, okay? I will leave you at the first stage of the tree, and I will let you walk your way down to see if you'll be able to get the pure leaf nodes, right? So what I will do now, I will erase this, and then let's start tracing our tree. So here, we got this, right? So what we have to do, we now take our outlook to be the root node. Hope that is clear. If you have any more doubts, feel free to get in touch with me. Then I will explain it again. All right? So our outlook now has become our root node. I hope I can be able to fit it in this. So outlook, no doubt. Now we know for sure. We know practically if a word like that exists. Okay? We know for sure that outlook is our root node. Now, outlook has other attributes, right? Sunny, rainy, and overcast. So, fine. So we branch it now. Sunny. Now, rainy and overcast. So why did this fellow put overcast at the center? Simply because I know that these two requires branching and this doesn't require branching. It doesn't matter, okay? You can put it here also, but just think of it. If I put sunny here and rainy here and overcast there, right? So it doesn't look nice, no? So I try to balance the three, right? So why do I say that overcast doesn't require branching? Because if you check, overcast has only one instance, which is positive. So overcast has gotten to the pure leaf node, which is, yes, Katam Hogia. So we don't need any further splitting, right? So this is my pure leaf. No further splitting, right? Now, how about sunny? If I go to sunny and rainy, So I need to know which one should come next, right? So that is where I will enter step 4. See, sunny and rainy. Why? If you go to sunny, you have yes, no. You go to rainy, you have yes, no. So I need to split these two. So then these two now need further splitting. So they need further splitting. Needs, I hope you can see the board, needs further splitting. Now, what we do is, again we repeat the process, okay? So we are going to repeat the same process, and I somehow request you guys to do what? To do it yourself, okay? So you repeat the process again, okay? And you will get something like this. After you finished, you get a subs table that will look like this. So this was the first table, right? This was the first table. First table, I mean table 1, table 1. So the next table will look like this, attributes and gain. I'm just giving the value so that we finish the tree, okay? Attributes and gain value, okay? So what are the attributes now? What are the attributes? Don't tell me Outlook. Outlook is out only, right? So we have temperature, humidity, and windy. So temp, humidity, and windy. Now, so in temperature, I'm just giving you the gain value, okay? That is the information gain value. So we got 0.57, 0.571. So 0.971 for humidity, 971. And 0.020, 0.020. Then we pick the one with the highest information gain, which is 0.971. So 0.971 is for humidity. So we come here now and we say, fine. The one that should come next is what? Humidity. Fine. So here I can put now sunny. 1 minute. So sunny. Yes. Right. So with that, yes, the next node becomes humidity. Okay. Please remember, humidity, see here, okay, it has the highest information gain, right? So we put it in that, right? So take care quickly. So we put here humidity, right? Now, humidity, what are the possible attributes? I mean, yeah, subsets of humidity. Go back to your table, go back to your table. You have only high and normal. High and normal. So high and normal. Now, high, check, check, check. Humidity, see, I didn't draw the table, okay? That's why I want you to follow along. You trace it, and then you'll be able to understand what we are doing. So, for humidity, for high, we had no, and for normal, we had yes. So, for high, it was no. We are done. Normal, it was yes. So, you see, this again are pure leaves now. So, we got another pure leaves. No further splitting, pure leaves. Practically, you know that what is left now is this last one, right? So what will be there now? So you see, humidity is out. So you have temperature and windy, right? Temperature and windy. So the next question is, which one should I choose? Should I choose temperature or windy? Again, you call the function, okay? So lastly, the table will look like this. I will draw the table for the last one. Normal was yes, and that was no. Fine. So the last table will look like this. Again, we have attributes and gain value, and the gain value. So we had temperature, humidity, and windy. Temp, humidity, and windy. So temp was 0.02, 0.02, humidity 0.02, yes, and windy 0.971, 0.971. So you see again, windy is the next node. So what I will do, I will update this now. Right. So this is split, done. I will update this. So what comes in there is windy. Windy. So windy, we had two sub-attributes, which is weak and strong, or strong and weak, if you've made the table. So weak and strong. So for weak, it was yes, and strong, no. Weak, yes, and strong, no. So again, we have obtained pure leaves. Pure leaves. So end of ID 3. End of ID 3 algorithm. So what happens now? Program terminates. We are done. Program terminates. Now, can you imagine how long it took us to compute this? So that's why we have lab, okay, where the professors will take you through how you execute this program from scratch. Please remember, we are not going to use any inbuilt function for the lab programs. So if you are in doubt, I request you to please trace this again. Don't assume that you know it, right? See, the essence of taking pains and writing it on the board is to reinforce whatever you have learned. Please no shortcuts. Don't say, okay, I have it in my system, I will just study from there only. Please trace it, even if it takes you 2 hours to complete it. Keep going, provided you don't stop. Remember, I will leave you with this quote, okay? It's not my quote, so I hope I have it, right? So, it was a quote by Warren Buffett. And you know Warren Buffett is regarded as the wisest investor to ever live. Warren Buffett said something, and I quote, he says, an idiot with a plan can beat a genius without a plan. I repeat, Warren Buffett says an idiot with a plan can defeat a genius without a plan. Thank you guys, and happy studying.